All right, let's do a Kepler's law problem. So we're going to do in your textbook, we're going to do page 243. We're going to do the second one, number 2. So that's the problem we're going to do. All right, so it says at what distance above Earth would a satellite have a period of 125 minutes? So we're going to use Kepler's law, Kepler's third law for this. So we want to find, number 2, what is the height above the surface, right? That's our altitude. The period of time, period is capital T, 125 minutes, which is the same as 7,500 seconds. And this is the mass of Earth. So this information, it's on the back of your formula sheet. It's also in some of the problems in the reading. So the mass of the planet is going to be 5.97 times 10 to the 24th kilograms. And the radius of the planet, I'm going to use little r for this, 6.38 times 10 to the 6 meters. So Kepler's law, which we're going to use, is the period of time, which is capital T, equals to 2 pi times the square root of, I'm going to use big R cubed, and that'll just be for the diagram that I'll show in a second, divided by big G and then M. So it's the square root of this stuff. Why am I using that big R? Look at this fancy tool. Because if we were to draw in a picture of Earth here, and here's the planet, there's the center, I'm going to label this R as the radius of the planet. Let's change some colors here. Let's use this one. And then this is where our satellite's going to be, up here. There's our satellite. And so this distance is h. What I'm doing is I'm calling this longer distance, this whole thing, I'm calling that capital R. Just so we have lowercase and capital so we can see the difference between the two. So I need to solve this equation here for R, big R, because if I know that big R is equal to the radius of the planet plus the altitude, which is height, if I want to solve this for height, my next step after this will just be taking R, big R, minus little r. So ultimately, I want to get here to this. So what I have to do then to solve this for r is I have to square everything. And if I do that, then I have t squared equals, I end up with 4 pi squared r cubed over big G m. So now if I just do a little rearranging to solve it for r cubed is going to be equal to t squared, big G, m, over 4 pi squared. And then to solve this for r, I have to take the cube root. So r will equal to, it'll be the cube root of t squared, big G, that's a G, m, over 4 pi squared. So this is the equation that I'm going to use to solve for this problem. So the first step is to find big R, which is the red R over here, and then I'll take the radius of the planet away from that, and I have my altitude. So R, big R, will be the cube root of, I've got my 7,500 seconds squared, and then big G, 6.673 times 10 to the minus 11, that's messy, 11, Newton times meters squared over kilograms squared. And then the mass of the planet, 5.97 times 10 to the 24 kilograms, divided by, whoa, not good, divided by 4 pi squared. So when I do the calculator stuff, to do this gives me 8.28 times 10 to the 6 meters. So that's what big R is equal to. That's this red R over here. So if I want to find the height of the satellite, the altitude of the satellite, then I'll use this equation where height will equal our big R, 8.28 times 10 to the 6 meters, and I'll subtract the radius of the Earth, 6.38 times 10 to the 6 meters, and then the ultimate answer that we get for this problem is going to be 1.90 times 10 to the 6 meters, which is 1,900 kilometers. So that satellite is way up there. Here's the answer right here. So nothing too fancy, I don't think. We've done much harder problems than this. Give it a try. There's a few things that will be posted. And I will talk to you later. Good luck.